This is the walkthrough video for PCTC 2023, question 9, round 2, question 9, line of coins. Okay, so we're given this input, which is just a line of coins, as the title suggests, and each coin is either heads or tails, and our goal is to, using the minimum amount of moves possible, to convert all of these coins so that they face heads up. And each move constitutes of flipping 2 adjacent coins. Okay, so let's first take in our inputs. So let's take in the length. I guess this is not strictly necessary because we can calculate the length ourselves, but oh well, take in the length. And now let's take in our coins. And we're going to take them in as a list because as our algorithm progresses, as our program progresses, we're going to change the value of each position. So whenever we flip over a coin, we're going to change the value of the coin in the list, which is just easy to do if we have the coins as a list as opposed to a string, for example. Okay, now for the algorithm. So we're going to pass from the left of our input to the right of our input, and whenever we see a tails, we're going to flip that coin and the next coin over. So we effectively get rid of the tails that we just saw. So now let's do for I in range length -1. And the reason we're doing -1 is because whenever we flip a coin over, we have to also flip the adjacent coin over. So we're going to flip the coin to the right of it as well. And that means we can't go right to the end of our coins list because then we'll run out of coins to also flip over and it just wouldn't be a valid move. And we know this algorithm will still work even if we only go to the penultimate coin because we're told that every challenge we're given will be solvable. And therefore, we know that this will work, even though it doesn't necessarily seem the most rigorous. But if a challenge is solvable, then line 4 is perfectly valid. Okay, now let's check if we are on a tails. So if coins I is equal to a tails, then we want to flip stuff. And if it's not a tails, then we just don't do anything. And so what we want to flip, we want to flip I itself to be equal to H. And we also want to flip I plus 1, so the next coin. But we don't know what the next coin is. It could either be heads or it could be tails. And what it is depends, will influence what we flip it to. So you could just have a couple of extra if statements to figure out what it is. But I'm going to do a one-line if statement, which is just a bit tidier. So I'm going to make it heads if it was equal to tails. And if it wasn't equal to tails, I'm going to make it tails. And so this is just the one-line if statement, which is just a bit cleaner in this case because it's not a very difficult if statement to code up. Okay, and that's pretty much our algorithm done. I guess the final thing to do would be to check, or I guess to count how many flips we've had. So not how many flips, sorry, how many turns we've had, because each turn is 2 flips. So let's set the turns variable to 0 at the beginning of the code, and every time we do a couple of flips, let's increase turns by 1. And at the end of the code, we can just print out turns. And that should be the correct answer. Yep, that seems to be working. Awesome. So at this point, you can kind of click off the video, but I'm going to talk a bit more about how I tried to solve this problem and why my approach perhaps wasn't necessarily correct. So this approach, this is called a greedy approach, like it's just greedy, like that. And it's called a greedy approach because at every stage in our process, in our algorithm, we're taking what seems to be the best move at that point in time. For example, every time we encounter a tails, at that point in time, we're just going to flip the tails to a heads. And my original solution to this problem was actually a BFS, or a bet first search, which is a graph algorithm. If you never come across that, think of it as, well, firstly, I have a video about that on my channel. And secondly, you can kind of think of it as this brute force solution, because it checks every single combination of flips until you reach your answer. And so it just checks every single possible combination that you can take, assuming the combination is valid. And then the first combination that leads to the desired outcome, which is just only heads, then that's going to be the answer. And that solution, that actually only got me 2 out of 10 points. I was just baffled for the longest time. So it got me the first 2 marks, but none of the other 8. And that perhaps suggested that maybe my solution was either too memory inefficient or too time inefficient, because in these tests, you're only given a certain amount of time and a certain amount of memory. And if your code doesn't run within those 2 constraints, then you're just not given any marks. And so obviously BFS being a brute force solution, I thought that perhaps that could be a solution, or that could be a reason. Although I wasn't entirely convinced that was a reason because n only goes up to 100,000, which is obviously quite a lot. But that means that at most you're maybe only having like, say, I don't know, 50,000 flips, which for a computer, 50,000 isn't such a big number. So I was a bit confused about why my BFS was taking so long. In retrospect, perhaps it wasn't the time issue, because when I ran the BFS myself, I would just input massive strings, and they all seemed to be taking just as quick. So maybe it was a memory issue. Maybe if I decided to code a DFS or a recursive solution, which, for reference, if you don't know, recursive solutions are usually more memory efficient than BFSs. So if I were to do that, then maybe my code wouldn't break the memory limit. But equally, DFSs usually tend to take longer to find the correct solution in a problem like this. And so maybe it would break the time limit in that case. And so I was just a bit confused, right? My BFS wasn't working, even though my algorithm was objectively going to work, right? It's a brute force, it's going to work. And I did try to code a couple of optimizations in my BFS, but it still wasn't getting me 10 out of 10. And so I eventually just decided to start from grassroots, start with this problem after someone suggested it to me, which is the greedy approach, which is the approach we have here, which is literally just the simplest approach from left to right, turning over tails as you see it, and obviously turning over the next coin, because that's how the rules work. And I was kind of baffled, like, why does this approach work and my BFS approach doesn't? I mean, I know why my BFS approach doesn't, but I'm confused as to why this works and this is why does this work in every single scenario? So the BFS solution obviously works in every single scenario because it's a brute force solution. But why does this solution work in every single scenario? It's not a brute force solution. And typically, greedy algorithms don't work in every single situation. So why on earth does this one work in every single situation? And I spent quite a while trying to figure this out. As you can see, it's 5 a.m., so I just spent a while trying to figure this out. And I still can't fully grasp this intuitively. I think there are a couple of somewhat logical arguments that I've come up with, but for each argument, I also have a counterattack, which just makes me question, how do I know this is going to work? And I'm still yet to fully understand this. So my explanation is not going to be great. If you have a better explanation, definitely please do reach out because I need to know. So I'm going to give you perhaps a few points that may help you understand why this works, a greedy algorithm, a greedy approach works, and maybe something clicks in you, maybe it builds an intuition for you. But honestly, I'm yet to do that to myself. So let's say we're given this situation. Our greedy approach, I'm going to talk about 3 different things. So the first thing I'm going to talk about is local and global optimization. Then the next thing I'm going to talk about is almost like this idea of sub-problems. Ignore my horrible handwriting. I'm a programmer. I don't handwrite. I always type. And the third thing I'm going to talk about is, what is it going to be? It's going to be like the target. And I know that doesn't make much sense, but it will make sense when I explain it. Okay, so those are 3 things I'm going to talk about. Let's move that list over there. So in terms of the first one, local versus global optimization. And essentially a greedy approach, the whole idea of a greedy approach is that it is purely a local optimization. Because at every stage in the process, you're optimizing for what you currently see. So you're optimizing for the local thing that you see. You're not optimizing for the entire problem. For example, if I had a long, complicated maze, if I had a greedy approach, I would always take the route or I would always go to the next cell that's closer to my end of the maze. But that in the end, for example, if I had, let's say, just a very rough cube like this, the start was at that top left, the end was at the top right, and maybe here I have a junction to go, say there or there. No, not there. I have a junction to go maybe there or upwards. And obviously upwards is further away from my end goal. And so my greedy approach would be like, you know what? I'm going to take this one. I'm going to go right. But the path on the right might actually end up being like this entire really confusing path. Whereas the path up here might actually just be a much quicker path. And so clearly the greedy approach didn't work here because the shorter path is that blue path as opposed to that purple one, even though the blue one originally went off course. So whilst the blue one at this point in time was not a local optimization, it ended up being a global optimization. And this is the crux of why a BFS works. This is what BFS is good for, because it finds the blue one before it finds that purple solution, because it values distance over local optimization. And in most cases, that usually ends up being the best optimization globally. And I thought that in the problem we're given up here, that would also be the best problem, the best solution, because there could, to me, there could very well be random cases where perhaps taking the greedy approach just doesn't work. Perhaps you go on some other random path And yeah, I'm just a bit confused about that. But the local approach seems to always work. And that's kind of ties into this idea that you can't like backtrack yourself. So like the reason, so like whenever a BFS or a DFS approach is useful, it's the idea when maybe if you're to do a recursive approach, you have to backtrack yourself. Like if I were to um, go find a dead end, I might have to backtrack myself and go back here. Or like if I ended up going like if I ended up reaching this point in my purple route, I've already taken so long, I might need to backtrack all the way back up my purple route and try the blue route. And this idea of backtracking is like kind of the idea that maybe you need to take an indirect route to get an overall better answer. And for some reason, that's not applicable in this problem that we're given in PCTC. And I still don't really understand why, to be honest. But that's just how it is. And maybe one explanation as to why that's the case is the idea of subproblems. So let me just demonstrate what I mean by that. So and again, this is kind of the idea of recursion. Whenever you have recursion, you break something into a smaller subproblem and solve that subproblem, and you keep doing that. But that's not really relevant in this case. So yeah, ignore what I just said. So subproblems. If I were given this entire string, and then I want to do some processing on it, so according to the algorithm that I just showed you in the editor, this algorithm, what it would do is it obviously ignore the h because that's an h, that's what we want, and then it would change the t, the next t, to an h. So that t would now become an h, and of course I'd also have to flip over the next coin, and so that would become a t. And so after, oops, there's one more t. Yeah. So after one turn, I get this. So after one turn, I'm left with this string of coins. And now, like another way of looking at this is that we've essentially just solved the problem up until our current coin. So the coin we just looked at was that coin. We just looked at that coin and we just processed that coin because we said if it was a t, we're making it an h. And so our problem is effectively solved for everything to the left of that breakpoint. So everything up until and including the thing we just looked at, our problem is solved because we know everything there is an h because our algorithm literally just says if we encounter a t, turn it into an h, which means everything up until our current point has been solved. And so you can think of it as if we've almost just created this new subproblem. Sorry, we almost created that new subproblem, which is this. And so we've already solved that part, and now we're only dealing with a subproblem. And you can kind of continue this logic, right? Because after you've done that first pass, that first turn, then the next turn you do is like, this is a t, and so you're going to be like, let me change that to an h. And also you have to change the next one, which also happens to be a t. And so after the next turn, we're left with this. And again, if you look at it, we've solved the problem up until everything that we've reached. So everything to the left of that breakpoint we've solved because everything here is the h, which is our goal. Everything to the right still requires processing. So perhaps this is a good way of maybe trying to understand why this is a greedy approach. Again, I still don't entirely understand it, but maybe this is a good way for you because, or maybe I'm missing something. Yeah, I could very well be missing something, and I probably am because I don't get it. So maybe this is a good approach because we kind of just discard everything to the left, and now we're almost saying, right, this is our coins list. That's all we care about at this point. And maybe like I don't really understand how this works though, because again, like maybe there might be an indirect route to getting our problem, to getting our solution. Clearly, there isn't ever an indirect route because the greedy approach worked. And I actually did some more testing to see whether the test cases here were just kind or whether the greedy approach actually always works. And it turns out a greedy approach actually does always work. I simulated hundreds of thousands of different strings, and every single one of them, you got the correct answer by both doing a greedy approach and by doing a brute force BFS. And so a greedy approach clearly works in every single case, which I am very intrigued by. And I don't know what else there is to say about this subproblem idea. I still you're just constantly breaking it down into smaller subproblems because everything up until that point is fixed, and it's fixed because you're one closer to your target. And that brings me on to my third and final point, which is the target. And this is my this is like the final explanation I can try and give you, which is that our target is obviously ultimately to change every t to an h. So every time we change one t, we're one closer to our target because our target is to change every t to an h. And so if we were to, for example, as we did up here, when we change this t, we're almost like one closer to our target. Obviously, in this case, we're not actually because we just we changed t to an h, but we also created a t. But generally speaking, we're like one move closer to our target or one t closer to our target. And that's especially relevant here, right? Because we've just changed a t or two, and now we're two moves closer to our target. And so this idea of a greedy approach always getting you one closer to your target, and that eventually getting the correct answer, like that kind of makes sense. And that's why people, if you've never heard of a BFS, you're probably always going to think of a greedy approach first to a problem, because that just makes sense. You want to get one closer to your target every single time, and this is what BFS does. Sorry, this is what a greedy algorithm does. But then you're subject to the same arguments I made up here, like the same counter arguments I made up here, which is that getting one closer to your target isn't always the best approach, as we saw in this maze example. And so why is that the best approach here? And I still don't really get it. And in fact, the first thing I said when I talked about the target is also kind of like another counter argument, right? Because in my first pass, when I change this t into an h, I'm not really getting one closer to my target, right? Like, sure, I've reduced the amount of t's from 4 to 3, but then I create another t over here. And so my amount of t's goes from 4 to 4. Like, that doesn't necessarily seem like I've reduced, or I've gotten closer to my target. And so I'm still a bit confused. And I think fundamentally, this perhaps works because the problem is just really simple. Like it's a 1D linear problem. There isn't much to it. There's just H's and T's. Whereas with a maze, it's 2D. There could be obstructions throughout the way and that type of thing. Whereas just with this problem, what you see is what you get. And maybe the idea of what you see is what you get is the reasoning why a greedy approach works in this case, and why there aren't many obstacles later on. I don't really know. I haven't come up with like a good way to almost like quantify or to objectify or to like write in like write clearly and concisely why this is a greedy approach and why this like works. I don't know. Maybe the answer is just because this problem is relatively simple in the grand scheme of things. Like what you see is what you get. It's I don't know though. Like what you see is what you get in the maze as well, though, because you're given your walls. I really don't know why this works, and I'm trying to build up an intuition for myself and hopefully for you. But obviously, I can't do it. If I can't do it for myself, I can't probably do it for you. Because whenever we see a problem like this, we want to know whether we can just do a BFS or whether we can save our time and just do a greedy. And in fact, in this case, if you did a BFS, you would have wasted so much time because the BFS doesn't get you the marks. And so you'd be stuck there, like me. You would have been stuck there for ages trying to get the correct answer before eventually just resorting to a greedy. And I don't know, maybe the lesson from this is to, if your BFS doesn't work, you should just try greedy. But the issue is, like, if your BFS doesn't work, it could just very well be the fact that your BFS is wrong. Like, you may have just messed up. And so you don't know whether you've messed up or whether your BFS is correct, but it's just too inefficient. And I don't know, I'm really confused here. Yeah, I just really don't know. I don't know whether I've been helpful with my explanations or my arguments or my counter arguments, but hopefully just giving you some food for thought about this whole idea of algorithms and stuff like that. And I absolutely love algorithms and data structures and this entire thing. That's why I make these videos. I think it's so cool. And this is like what I like diving straight into. So even though I'm still really lost, even more lost at the end of this video than I was at the start, I don't know. I've enjoyed thinking about it. Hopefully you've enjoyed thinking about it, and hopefully you're confused or you've found some clarity in why a BFS doesn't. Why a greedy algorithm works. Because a BFS does work, but greedy algorithm also works, and it works better. And yeah, I'm just kind of confused there. But anyway, this is a problem. This is my solution. This is kind of the solution that you need. And it runs in linear time, so it's probably as efficient as it can get. If you know what big O notation is, it's O to the n. So it's obviously really good. But yeah, if you have any insights into this problem, please reach out. But otherwise, enjoy.